Okay, here we have an integral. Nice calculus practice. The integral of x to the fourth, etc., over x to the square, etc. Two polynomials. Notice the numerator has the higher exponent, so we're not going to be using partial fractions right off. We may get that in later, but not right now. So what are we going to do? Well, looking into your table of integrals isn't going to help you. There's not really much one can find looking at this. Of course, in calculus, always remember your algebra. Your algebra is your friend. Also your trig, but we don't use that here. So we make the long division, x squared plus x minus 2 into x to the fourth plus 3x cubed plus 3x squared plus x minus 5. Well, I would hope that you can all follow the steps. If not, pause it and please read it. You end up with a quotient x squared plus 2x plus 3 and a remainder 2x plus 1, which we'll write over x squared plus x minus 2. So now our integral looks like this. Whoa, now we're starting to see we have something we can handle. Certainly we should be able to handle this. X to the n. And here we would hope this factors, and I will tell you now it does. But even if it didn't, we could use the quadratic formula. And so we're going to do partial fractions on this term. So now let's take a look. We're going to look at this part, temporarily ignoring the constant of integration because we will have one constant of integration at the end of the problem. I'm not going to write plus C1 plus C2 and add them together. We're just going to say plus C at the end. Well, the integral of x squared is x cubed over 3. The integral of 2x is 2x squared over 2, and of course the 2 is canceled, so that's just x squared. And the integral of a constant, 3, is just a constant times x, so that's 3x. That part is done. So now we're going to take a look at the remainder, 2x plus 1 over x squared plus x minus 2. We are going to factor the denominator in preparation for partial fractions. So we have x plus 2 times x minus 1. So the technique is, I'm going to claim that I can decompose this fraction into two fractions. I'm going to have some numerator a and some numerator b. I don't know what those are just yet. So I'm going to have a over x plus 2, one of the factors, plus b over x minus 1. So this fraction has to equal this fraction. The denominators are equal, so the numerators have to become equal. So let's look at the x terms. 2x, ax, and bx. So well, what I have is ax minus a plus bx plus 2b. So ax minus a plus bx plus 2b equals 2x plus 1. And I was getting a little ahead of myself. I want to look at the x terms. Okay, so if I look at the x terms, I got a plus b equals 2. And if I look at the constant terms, I get negative a plus 2b equals 1. Now, they won't always work out this nicely. Here, if I just add the two equations, treating a and b as the variables, the a's disappear, and I get 3b equals 3. Well, if 3b equals 3, I get b equals 1. Now I can go back to either of these two equations and substitute the 1. So this one looks nice since it has a positive number, but it's not really that hard with the negative. A plus 1 equals 2. Well, the problem is now, can I subtract 1 from each side? And I don't even need my calculator for that. A equals 1. Well, if I substitute for A and B, I have 1 over x plus 2 and 1 over x minus 1. Well, you recognize that if I let u be x plus 2, du is simply dx, and so I have a logarithm. So I have the logarithm, the natural log of the absolute value of x plus 2. Likewise, I can let u be x minus 1, or v if you want to have a different variable, and v then would be dx. I get the natural log of the absolute value of x minus 1. So I'm going to take this part and the part I already found and get my answer. So the overall integral is just going to be x cubed over 3 plus x squared plus 3x plus the natural log of the absolute value of x plus 2 plus the natural log of the absolute value of x minus 1. And now I'm going to finally put it plus c. It must be put. This is an indefinite integral, so it does have to be part of the answer. I just deferred adding it at the individual steps.